The first thing people noticed was the sound. A deep tearing crack, not sharp like a branch snapping, but long, heavy, as if the forest itself was splitting under pressure. A steel cable tightened. A steam donkey engine hissed at around 120 pounds per square inch, its piston hammering back and forth with a dull metallic rhythm. And then, a tree nearly 90 meters tall began to move, not fall, move, slowly, reluctantly, as if something that had been fixed in place for centuries was being forced to change its mind. For decades, this moment has been presented as something simple, a machine, a tree, a clean cut, a symbol of progress. But when you look closely at what actually had to happen to move a 100-ton tree, the simplicity starts to disappear. In most historical accounts, the story is straightforward. Forests were vast, demand for timber was growing, and new machines made it possible to harvest wood faster than ever before. Steam-powered sawmills, mechanical logging systems, rail-based transport lines cutting through dense wilderness. The narrative is clean. Before machines, labor was slow, inefficient, limited. After machines, productivity increased, costs dropped, and entire industries expanded. In classrooms, this is often framed as part of a broader transformation. Industrialization didn't just change factories, it reshaped landscapes. Entire forests could now be processed at a speed that earlier generations couldn't have imagined. In museums, you see it as scale. Photographs of massive logs, workers standing on top of tree trunks wider than their own height, machines that seem oversized, almost exaggerated. Everything points to the same conclusion. Humans finally had the tools to control nature. But that version of the story usually skips one detail. A 100-ton tree doesn't behave like something that wants to be moved. When a tree of that size was cut, it didn't simply fall and lie still. The trunk could measure over 3 meters in diameter. The internal tension, built up over decades of growth, could release unpredictably. Wood fibers twisting, sections splitting under their own weight. In some cases, logs would roll, not slowly, but with enough force to crush anything in their path. And yet, the narrative we're used to hearing rarely focuses on this. Instead, it emphasizes control, precision, efficiency, machines cutting through wood as if it were a manageable, predictable material. Logging systems in the early 1900s are often described as breakthroughs. Steam donkeys pulling logs with cables stretching hundreds of meters. Temporary railroads assembled deep inside forests. Teams coordinating movement between sawyers, rigging crews, and engineers. From a distance, it looks organized, systematic, almost elegant. But the closer you get to the actual process, the harder it becomes to describe it that way. Because nothing about moving a tree of that size was ever fully controlled. A single steel cable under tension could snap with explosive force. Whiplash speeds exceeding 150 kilometers per hour, enough to cut through flesh, bone, even small trees nearby. Steam engines didn't respond instantly. Valves had delay. Pressure fluctuated. Communication between workers often relied on hand signals or whistles over the constant noise of machinery. Still, this is not how the story is usually told. In textbooks, the focus remains on output, board feet of lumber produced per day, expansion of rail networks, growth of construction industries. The narrative reinforces a familiar idea. Machines made things better, faster, more efficient, more modern. And to some extent, that's true. Timber production did increase. Infrastructure did expand. Entire cities were built using materials harvested through these systems. But when the story is presented this way, something subtle happens. The machine becomes the main character, not the process, not the environment, not the people working within that system. The steam donkey becomes a symbol. The sawmill becomes a milestone. The log becomes a unit of output, and the act of cutting and moving a 100-ton tree is reduced to a step in a larger narrative of progress. But if this machine truly represented progress, if it really marked a clean transition from limitation to control, then why do so many physical details of how it actually worked? The instability, the unpredictability, the conditions on the ground rarely appear in the version of history most people are familiar with. If the story were only about efficiency, the records should be simple. More machines, more output, more control. And to some extent, that is exactly what the numbers show. In the early 1900s, logging operations in North America began to scale rapidly. Steam donkeys could pull logs weighing 50 to 100 tons across uneven terrain. Cable systems stretched 200 to 400 meters through dense forest. A single setup could move multiple massive logs in a single hour. Compared to earlier methods, oxen, manual hauling, river drift, the increase in productivity was dramatic. But when the same records are examined more closely, another pattern appears. Accident reports begin to show up alongside production data, not as central information but as side notes, short entries, often only a few lines. A cable broke during operation. One worker struck by rolling log. Fatal injury during yarding process. There is rarely detailed explanation, no extended analysis, just documentation, and the frequency is difficult to ignore. In some logging camps, injury rates were among the highest of any industry at the time. Workers operated inside a system where tension, weight, and movement were constantly interacting, but rarely fully predictable. Consider the steel cables used in steam logging systems. They were often 2 to 4 centimeters thick, placed under extreme tension during operation. When a log was pulled uphill, the cable did not simply carry weight. It stored energy. If it snapped, that energy was released instantly. The result was a recoil effect that workers referred to as a whiplash zone. A cable could snap back at speeds exceeding 150 kilometers per hour. There was no clearly defined safe distance, and yet workers had to remain nearby to guide, attach, and release logs during operation. The system was productive, but it was not stable. Training manuals from the period did not describe a safe system. They described a dangerous system that required constant awareness. Workers were instructed to never stand in line with the cable, watch for changes in tension, anticipate log movement before it happened. These instructions were not about optimization. They were about survival. Even the trees themselves introduced uncertainty. A 100-ton tree did not fall cleanly. Internal stresses, built over decades of growth, could release unevenly. The trunk could split during the fall. Sections could twist. Fragments could break away and travel in unpredictable directions. In some cases, trees did not fall in the intended direction at all, despite careful cutting, despite wedges, despite experience. And once the tree was on the ground, the unpredictability did not end. Logs could roll, shift suddenly, or slide downhill if the ground beneath them gave way. This meant that moving the tree was not a single action. It was a sequence of unstable events. Each one required coordination. Each one carried risk. However, in most versions of the story, this complexity is rarely emphasized. Instead, the focus remains on systems, steam-powered efficiency, mechanical advantage, industrial organization. When different types of records are compared, a small inconsistency begins to appear. Production reports emphasize output, volume, speed, growth, but field reports, notes from engineers, supervisors, and workers often describe something else. Delays caused by terrain, equipment failures, unpredictable log behavior, weather conditions affecting traction and visibility. In wet conditions, logs became extremely difficult to control. Mud reduced friction, cables slipped, anchors shifted under load. Entire systems had to be adjusted in the middle of operation. And yet, the system continued to be described as an advancement in control. This does not mean the machines were ineffective. They clearly were. They allowed material to be moved at a scale that had never been possible before. But effectiveness and stability are not the same thing. This is where the narrative begins to feel slightly misaligned, because the dominant story suggests a transition from limitation to precision, from uncertainty to control. But the technical details suggest something else. A system where power increased dramatically, while unpredictability remained. A system where output expanded, but risk did not disappear. It changed form. And yet, when this period is described in most historical accounts, these two aspects, productivity and instability, are rarely presented together, which leads to a simple question. Why does one set of details appear clearly in technical documents, while the other barely appears at all in the way this story is usually told? By the early 20th century, The machinery used to cut and move massive trees was already being described as a turning point in industrial history. In textbooks, logging systems were often presented as a clear example of technological progress. Manual labor replaced by machines, unpredictable effort replaced by controlled force. Nature reorganized into a system of inputs and outputs, but when different types of records are placed side by side, the clarity of that narrative begins to soften. Engineering documents from the period do not describe a fully controlled system. They describe limitations. Steam donkey engines, for example, were powerful but inconsistent. Operating pressures could fluctuate depending on fuel quality, water levels, and maintenance. A drop in pressure, even by a small margin, could reduce pulling force significantly, which meant that moving a 100-ton log was not always a smooth, continuous action. It often happened in bursts. Pull, stop, adjust, pull again. This stop and start movement introduced additional instability. Logs could shift direction between pulls. Cables could re-angle under load. Anchors, often large trees or buried stumps, could loosen in soft ground. These details appear repeatedly in technical descriptions, but they are rarely emphasized in simplified historical narratives. Another example appears in cutting methods. Large trees were not simply cut down by a single machine. In many cases, teams used long crosscut saws, often over 2 meters in length, operated by 2 workers. The process could take hours, sometimes longer. During that time, workers had to predict how the tree would fall. They used wedges. They adjusted cutting angles. They listened to the sound of fibers tearing inside the trunk. Even then, the result was not guaranteed. This contrasts with the common image of industrial logging as a clean mechanical process. A machine engages, the tree falls, the system proceeds. But in practice, the act of cutting remained partially manual, partially interpretive. Photographs from the period are often used to reinforce the idea of scale and control. Massive logs, organized work crews, machines positioned with apparent precision. But photographs capture moments, not processes. They do not show the hours of preparation, the failed attempts, the delays caused by terrain or weather, the repeated adjustments required to move a single log. This creates a subtle distortion. The visual record emphasizes outcomes. The technical record describes conditions, and the two do not always align. In popular narratives, machines are often described as replacing human labor. But in logging operations, the relationship was more complex. Machines increased the scale of work, but they did not eliminate the need for human judgment. Workers were still required to position cables, guide logs, monitor tension, interpret movement in real time. In some cases, the introduction of machinery actually increased the intensity of labor, because instead of moving smaller loads manually, workers were now responsible for managing much larger forces. A 100-ton log under tension was not simply heavier, it behaved differently. Momentum increased, reaction times decreased, mistakes became less forgiving. This is rarely highlighted in simplified narratives. Instead, the emphasis remains on machines liberating workers from physical strain, which is partially true, but it does not fully capture the shift in the type of risk involved. Another point of exaggeration appears in the idea of speed. Industrial logging is often described as dramatically faster than earlier methods, and in terms of output, that is accurate. But speed at the system level does not always mean speed at the task level. Individual operations, cutting, rigging, repositioning, could still be slow. Careful, repeated. Delays were common. Adjustments were constant. What changed was not that everything became fast, but that the system could process more material over time. This distinction is subtle, but important, because it challenges the idea that mechanization created a uniformly efficient process. Instead, it suggests a system that combined high output with ongoing friction. Finally, there is the question of timing. Popular narratives often present industrial logging as a rapid transformation, as if forests were quickly reorganized once machines were introduced. But historical records suggest a more uneven process. Mechanization spread gradually. Different regions adopted different methods. Older techniques continued alongside newer systems. In some areas, manual and mechanical methods coexisted for decades. This does not fit neatly into a linear story of progress. It suggests overlap, variation, adaptation. And yet, when this history is summarized, these irregularities are often smoothed out. The result is a narrative that appears more coherent than the underlying process. Machines are presented as decisive turning points, but the document suggests they were part of a longer, less uniform transition. None of this means the machines were unimportant. They clearly changed the scale of what was possible. But the way that change is often described, as clean, immediate, and fully controlled, does not fully match the technical and historical record. What we see instead is a pattern. Certain details are emphasized, scale, output, mechanical power, while others are reduced or omitted. Instability, partial manual dependence, uneven adoption, and shifting forms of risk. And over time, those omissions begin to shape how the entire process is understood, not as something complex and conditional, but as something resolved. Which raises a broader question. If the story of these machines became simpler over time, was that because the process itself was simple, or because the complexity was gradually left out of the way the story was told? By the time large-scale logging systems became established in the early 20th century, the machines themselves were no longer just tools. They had become symbols. A steam donkey pulling a 100-ton log through a dense forest was not only a technical achievement, it was a visual statement. Power, control, expansion. And over time, that image began to carry meaning beyond the work itself. In industrial exhibitions and public displays, machines like these were often presented as evidence of advancement, not only economic, but civilizational. Large-scale extraction of natural resources was framed as a sign that a society had reached a higher level of development. Forests being transformed into lumber were not only supplying material, they were demonstrating capability. In that context, the narrative of control served a clear purpose. It showed that nature could be organized, measured, converted into usable output through engineering. And this idea aligned closely with the interests of growing industrial economies. Expanding industries required consistent narratives, stories that could justify scale, stories that could present growth as both necessary and beneficial. The image of machines operating with precision and efficiency fit that requirement. It suggested that expansion was not chaotic, but structured, planned, rational. This did not require exaggeration in a deliberate sense. It required selection. Certain aspects of the process were easier to communicate. Large machines, clear outputs, visible results. Other aspects were harder to integrate. Instability, unpredictability, working conditions that did not align with the image of control. Over time, the easier elements became the dominant story. This pattern can also be seen in how governments and institutions presented industrial development. In many countries, industrial growth was closely linked to national identity. Railroads, factories, and logging systems were presented as signs of modernization, evidence that a country was progressing. In that context, machines were not neutral. They were representations. A logging system capable of moving massive trees across difficult terrain could be framed as proof of technological competence, and by extension, as proof of national strength. This did not require ignoring reality, but it did encourage a particular emphasis. The parts of the story that reinforced progress were repeated. The parts that introduced ambiguity were less visible. A similar pattern appears in industrial companies themselves. Large-scale logging operations required investment, infrastructure, coordination across multiple systems. To sustain that, the activity needed to be understood as efficient, predictable, scalable. The image of machines operating smoothly within a system supported that understanding. It made the process easier to explain to investors, to regulators, to the public. Again, this did not require fabrication. The machines were real. The output was measurable, but the framing mattered. Describing a system as controlled is different from describing it as conditionally managed. One suggests stability, the other suggests ongoing risk. And over time, the more stable version became more widely repeated. Even outside of industry and government, this pattern continued. In education, complex processes are often simplified to make them easier to teach. A sequence is created: before, after, improvement. In that structure, machines fit naturally as turning points. They provide clear markers, moments of transition, But that structure does not easily accommodate overlap, inconsistency, or gradual change. So those elements tend to be reduced, not removed entirely, but made less central. Museums follow a similar logic. Exhibits are designed to communicate clearly. A large machine placed in a gallery space can represent an entire process. Visitors see scale, design, function. What they do not see is the environment in which the machine operated, the terrain, the weather, the continuous adjustments required to make the system work. The exhibit becomes a summary, and in that summary, the machine appears more self-contained than it ever was in practice. Over time, these different forms of presentation, industrial, educational, institutional, begin to align, not because they are coordinated, but because they are compatible. They all benefit from a version of the story that is clear, structured, and easy to communicate. A version where machines represent progress, and where complexity is present, but not central. This does not mean the narrative is false. It means it is selective. It highlights certain elements while reducing others. And once that selection is repeated across multiple contexts, textbooks, exhibitions, reports, it begins to feel complete, even if parts of the process remain outside the frame. Which leads to a different kind of question. If this version of the story is easier to communicate, easier to teach, and easier to align with broader ideas of progress, what happens to the details that do not fit that structure? And more importantly, were those details ever absent? Or were they simply less likely to be included in the way the story was told? When the broader narrative is set aside and the focus shifts to primary records, the tone of the story changes. Not dramatically, but noticeably. In logging reports from the early 1900s, the language is rarely symbolic. It is functional, measured, focused on conditions, instead of describing machines as instruments of progress. These documents describe systems that had to be managed continuously. Engineering notes often refer to adjustments, cable tension recalibrated after each major pull, anchor points reinforced when soil conditions shifted, steam pressure monitored constantly to maintain consistent output. None of this suggests a fully stable system. It suggests a system that required ongoing correction. Worker logs provide another layer. Entries are brief, sometimes incomplete, but patterns emerge over time. References to fatigue, repeated delays, unexpected log movement, equipment strain under heavy loads. The language remains technical, but the repetition of these details creates a different impression than the simplified narrative. Accident records are even more direct. They do not describe causes in abstract terms. They describe events: cable failure under load, log shifted during repositioning, worker caught in line of pull. These entries are not rare. They appear regularly, across different sites, across different years. In some reports, accidents are categorized by type: cable-related incidents, crushing injuries from rolling logs, falls during rigging operations. The classifications are systematic, which suggests these were not isolated events. They were recurring conditions within the system. At the same time, production data continues to show growth: higher output per day, increased volume transported, expanded logging areas. Both sets of data exist in the same records, but they are rarely presented together. Technical manuals from the period offer another perspective. They do not describe ideal systems. They describe constraints. Instructions emphasize how to position workers relative to moving cables, how to read tension changes through vibration and sound, how to anticipate log behavior based on terrain and angle. These are not procedures for operating a predictable machine. They are guidelines for working inside a partially unpredictable environment. Even maintenance records reflect this. Frequent cable replacements, wear on pulleys and drums, stress fractures in metal components. These are not signs of failure. They are signs of continuous strain within the system. Weather reports are sometimes included in operational notes. Rain affecting traction, cold temperatures altering material behavior, fog reducing visibility. Each of these factors introduced additional variables, and each required further adjustment. Taken together, these documents do not contradict the idea of technological advancement. The machines clearly increased capacity. They enabled new forms of work at a larger scale, but they describe that advancement in a different way, not as a transition from disorder to order, but as a shift into a more complex system, one where power increased, but coordination became more demanding, one where output expanded, but conditions remained variable. The details were always recorded. They were written into reports, logged in daily notes, categorized in accident summaries. Nothing about them was hidden, but they were rarely integrated into the main narrative. Instead, they remained within technical contexts, separated from the broader story that emphasized progress and control. The separation creates a subtle effect. It allows two versions of the same process to exist simultaneously, one that is widely known and one that is consistently documented, but less frequently discussed. The difference between them is not based on new evidence. It is based on selection, which leads to a final observation. These data were always available. They were not discovered later. They were not uncovered after the fact. They were part of the system from the beginning. What rarely happened was bringing them together into the way the story was commonly told. And when they are placed side by side, the process does not become less significant, but it does become less simple. If the familiar version of the story is set aside, the clean sequence of progress, the image of control, the idea of machines as decisive turning points, what remains is not a different story. It is an incomplete one. The machines are still there. Steam donkeys, steel cables stretched across forest terrain, saws cutting through trunks over 3 meters wide, logs weighing close to 100 tons being pulled across unstable ground. None of that disappears. What changes is how those elements relate to each other. Instead of forming a clear progression, they form a system where power and instability exist at the same time, where increased capacity does not remove uncertainty. It reorganizes it, where control is not absolute but conditional, dependent on terrain, weather, material behavior, human coordination. In that system, machines do not replace complexity. They interact with it, and sometimes they amplify it. The idea that technology moves history forward in a straight line becomes harder to maintain, not because it is entirely incorrect, but because it is incomplete. The records do not suggest a simple transition from limitation to mastery. They suggest overlap, manual skill existing alongside mechanical force, predictable output coexisting with unpredictable conditions, stability in results paired with instability in process. When these elements are considered together, the role of the machine changes. It is no longer the central explanation. It becomes one part of a larger arrangement, one that includes environment, materials, and human judgment. This does not reduce the importance of the machines. They clearly altered scale. They changed what could be built, transported, and produced. But they did not simplify the underlying system in the way the narrative often suggests. Instead, they shifted where complexity existed, from visible effort to less visible coordination, from physical limitation to dynamic risk. And when the narrative is removed or reduced, what remains is a process that is harder to summarize, less linear, less stable, less certain. Some details become unclear. How much control was actually achieved in real working conditions? To what extent did machines reduce risk or redistribute it? How consistent was this system across different regions and environments? The records provide fragments of answers, but not a single unified explanation, which may explain why the simplified version became more common, not because it replaced the evidence, but because it organized it into something easier to understand and easier to repeat. But if, for so long, we have accepted a version of technological history that appears ordered, consistent, and resolved, what happens when we begin to look at the details that do not fully fit that structure? And if this pattern appears here, in something as concrete as cutting and moving a 100-ton tree, how many other histories are we still repeating simply because they align more easily with the narrative of progress?